Okay, so next week is our last official class for NR 493, and we have a panel discussion with Warner College recent graduates who got jobs in the geospatial field. So it's a career panel, but with like super early professionals. And I see Sophia Lynn here. It's going to be like a Centroid reunion because all 4 of them are Centroidians. So that will be next week if you're interested in hearing about that, and I'll post it in the usual places as well. So with that, I think we're ready to get started. So I'm excited to introduce our 2 guest speakers for today, Jennifer Boehnert and Olga Wilhelmi, who are from NCAR, National Center for Atmospheric Research. And they do really cool stuff with GIS and atmospheric and climate data. And they presented, I think it was 2 years ago at the Esri User Conference in the Science Symposium, all these like sub things, correct me if I'm wrong, in the Science Symposium. And this is basically the presentation that they will be doing for us today. And just fast fact here. So I actually used to teach at Esri like a million years ago with Jen. She was a trainer with me. And then she moved to NCAR and became to do great things. So with that, I will let it over to you. And thanks so much for presenting for us.
All right, well, thanks so much for the introduction, Beth. So Jen and I are actually going to tag team. So we have a number of slides that we're going to show you, and we're going to go kind of back and forth. And, you know, definitely we'll leave some time for questions and discussions. So again, thanks for the introduction. You know, we're very happy to present it in this seminar. As Beth mentioned, I'm Olga Wilhelmi. I'm a research scientist at NCAR, and I work on weather, climate, and society interactions with the main focus on risk, vulnerability, and resilience to weather extremes and climate change. I also use GIS as a tool for interdisciplinary research and science communication.
Yeah, and I'm Jennifer Boehnert, and as the GIS coordinator, I lead NCAR's research and development in geospatial technologies with a focus on integrating multidimensional atmospheric data with traditional GIS data and analysis tools to support Earth system science and interdisciplinary research.
So Jennifer and I are both geographers by training, and for the last 17 years, both of us have been working in the GIS program in the Research Applications Lab at NCAR. And I think we make a really good team because we bring complementary expertise in science and technology. And through this collaboration, we're not only enabling new scientific advancements and supporting different projects, but also contributing to expanding the GIS technology in the new dimensions.
And when I started at NCAR 17 years ago, GIS was new to atmospheric science. And it's so great to see the progress that's been made in regard to data interoperability in support of multidimensional data and the growing interest in the GIS community in weather and climate.
So what exactly is NCAR? I'm sure many of you have been to Boulder and maybe visited NCAR. But for some of you, if you're not familiar with our organization, so we are not NOAA, we are not the government, but we have many government sponsors, including the National Science Foundation, who is our primary sponsor. So scientists at NCAR study Earth system, and not only the atmosphere of the Earth, but its connections with the oceans, the land surface, and even the sun. And so with better understanding of this relationship, which the scientists model and observe, allows us to better serve society by providing the predictive capabilities and applications needed by a range of stakeholders to plan for the future.
NCAR provides national resources and facilities to many universities. These facilities include research aircrafts for advancing airborne research, as well as supercomputers for advancing the Earth system science. Our newest supercomputer is named Derecho, and its name was picked out of more than 200 submissions from Wyoming K-12 students. And we also develop community models at the global climate scale, the regional climate scale, and the mesoscale for predicting future climate and forecasting weather.
So almost 50 years ago, an American atmospheric physicist, astronomer, and philanthropist, Walter Orr Roberts, who was the founder of NCAR, said that it's wonderful to have the opportunity given us by society to do basic research, but in return, we have a very important moral responsibility to apply that research to benefiting humanity. And this quote really resonates with the lab where Jen and I work, which is Research Applications Lab. And this is a lab where scientists and engineers develop innovative solutions to address many societal problems. And this includes interdisciplinary, actionable, and convergent research where we focus on societal needs, conduct research that contributes to fundamental understanding of physical and social systems, and use and develop new technologies to support decisions and actions.
And GIS is an integral part for addressing societal challenges, given all the advancements in geospatial computational science and visualization techniques.
So I'm sure you have heard many times that the human footprint on Earth is expanding, and our world is changing at an incredible rate. So the world population expected to reach 9.8 billion by 2050. And with more and more people living in cities, we see more pressure on natural resources and also increased demand for water, for food. There are some concerns about energy security and global health. And climate change is also one of those pressing challenges that affects society worldwide, as also intersects with many of those pressing demands. There's also scientific concern that climate is changing. Human activities have caused approximately 1 degree Celsius of global warming above the pre-industrial levels. And if this warming continues at the current rate, we are likely to reach 1.5 degrees centigrade, somewhere between 2030 and 2050. So you can see on this animation from the NCAR community climate model simulation that shows a temperature anomaly, the warming greater than global annual average is being experienced in many land regions, including 2 to 3 times higher in the Arctic. Observed and predicting change in the climate system not only affect the global planet as a whole, but it also affects the weather, especially the weather extremes, and that's how most people actually experience climate change, through the weather extremes.
Climate-related hazards have always been a part of human lives. With global climate change, patterns in these climate and weather hazards are expected to change. According to the IPCC, new and strong evidence confirms that some of these increases are related to human activities, and we may see increases in frequency and intensity of weather disasters.
And this increasing number of weather extremes also increases the risk to society and the cost. This past several years have been historic, with the annual average number of billion-dollar weather disasters being more than double of the long-term average. You can see on this image from NOAA that this past year has been one of the record years and one of the costliest year in terms of weather disasters. And in particular, as you remember, they have been one of the record number of tropical storms and hurricanes that affected US East Coast and the Gulf of Mexico. And the hurricane, this sort of very active hurricane season produced some of the significant impacts, including high winds and significant storm surge to many communities. And storm surge is not only costly, it also accounts for nearly 50% of hurricane-related human mortality in the US. In this growing coastal population and projected sea level rise, many coastal communities are facing important adaptation decisions in the long term, especially given the uncertainty associated with climate, with sea level rise, and some of the changes in the storm's characteristics. But in the short term, people are looking for information that can help them better understand their risk and make decisions about protective actions. So despite improvements in the hurricane forecast, and you can see on this graph that shows the forecast for Hurricane Irma that happened a couple of years ago, that despite the cone of uncertainty, the actual track for the hurricane was really close to the predicted track. And nevertheless, the storm surge forecast remain challenging. And because of the different storm surge characteristics, the storm size, location, and so on. So even though the scientists can better predict the hurricane track, predicting storm surge in any particular place and time and the amount of flooding that can take place in a particular location still can be really challenging. And so there's definitely need for more effective risk communication given all of this uncertainty and the very dynamic nature of the storm.
With the advancements in GIS, we can now start integrating realistic landscapes and storm surge model output to better represent the hazard. Using 3D environments, we can communicate the risk and the threat from storm surge. This animation not only represents hazard as a two-dimensional, but also it communicates the temporal aspect of storm surge. Within a 15-minute time span, large areas of the coastal community can be flooded. This animation was created in Esri's City Engine. The 3D environment was built using real 3D data along with the high-resolution storm surge model. City Engine is now connected with ArcGIS Online and ArcGIS Pro for easier interoperability between all the platforms.
So another dynamic and very dangerous weather hazards are wildfires. And all of us have experienced some of the risks and threats from wildfires just even in the last year. Wildfire behavior is complex, and with warmer temperatures and drought in concert and decreased fuel moisture, we see some increase in lightning ignitions, and also we see increase in the period over which fires occur. So climate change is expected to continue to increase temperatures, reduce moisture, especially across the Western United States, and that can create preconditions for more intense fires. And not only the number of wildfires has increased over the years, as you can see on this graph, the number of large fires with some of the complex fire behaviors and significant damages has increased as well. And as well as similar to hurricanes, the goal of our group, of our research team, is to develop some of the predictive capabilities for the population at risk, as well as for the first responders, incorporating different characteristics of weather and environment into those predictions and visualizations.
An exciting new area of research and development is delivering real-time fire forecasts to firefighters in the field. These forecasts communicate timely information about the rate of spread, flame length, fire perimeter, and the changing weather. The model simulation simulates fire behavior based on weather forecasts, land surface characteristics, infrastructure, and fuel moisture, and it can be output and visualized in a GIS framework. This particular fire simulation is from the Cold Springs fire, which occurred in Nederland, Colorado in 2016. In fact, this is my neighborhood, and it was due to the incredible actions of the firefighters that most of the homes in this neighborhood were saved.
So as we just mentioned, fires very closely linked to fuel, the fuel and availability of moisture and droughts. And so even though droughts maybe don't ignite like fire or spread very quickly like fires, they can still leave a lot of destruction, devastation, and produce a number of agricultural, hydrological, and social impacts. Colorado has been in drought for many years now and is definitely something that many communities in our state are familiar with. And so again, drought and water deficits are projected to be one of the higher risk climate impacts for many cities and communities across the world, as well as in our state.
Visualizing a simulated drought index that's based on climate model simulations is a powerful way to communicate the spatial temporal patterns of drought. We're able to focus on how drought will intensify and the frequency of drought in certain regions of the world. This animation represents a 3-year running average of the Palmer Drought Severity Index for historical and future projections. The data being visualized was natively a 200-year global model output at a weekly timescale and a spatial resolution of 0.5 degree. This is a really large data set to bring into GIS. We therefore created this 3-year running average from the weekly data in order to make the data more useful and to convey the message that we were trying to tell. Take a look at Central and South America. Starting in the 1950s, drought becomes much more intense and more frequent in this region. Now take a look at Europe. By 2080, drought is much more widespread and much more severe.
So another weather hazard that sometimes don't get a lot of attention on the news, but actually one of the leading causes of weather-related human mortality is heat wave. And heat wave or extreme heat event is a period of unusually hot weather that typically lasts 2 or more days. Sometimes it can last several weeks. And usually during the heat wave, the temperatures have to be outside of the historic averages for the given area. Heat waves are much more prominent or could be more felt in cities where the heat island effect changes how people feel the heat compared to some of the rural areas. So we're going to take a little bit closer look at the heat in the next few slides. So we talked already about the increase in global average temperature, and here's another look, another animation from the NCAR Community Climate System Model, where we can see the difference in the annual surface temperature in the current climate compared to the late 19th century. So it's important for us to observe and model any changes in the average temperature, because even small change in the mean can lead to the large changes in the extremes.
We're taking a look at a temperature anomaly here. And what an anomaly is it's a deviation of a meteorological variable from the normal. In this example, normal is a 20-year base period of 1850 to 1899. Anomalies help us visualize general climate trends and assess degrees of change. Making climate science and climate science output more accessible to everyone is one of NCAR GIS's program's mission. One way to communicate the science is through developing state-of-the-art visualization tools, such as these interactive websites. These websites are based on our inspector platforms. The inspectors use maps and graphs to visualize the spatial and temporal dimensions of climate model output. The image on your left is the Climate Inspector. This is an interactive web application that expands GIS mapping and graphing capabilities to visualize possible future temperature and precipitation change. The maps and graphs are generated from a large data set of climate simulations that were prepared for the 5th assessment report for the IPCC. With the Climate Inspector, you can explore climate change around the globe, take a look at climate trends, variability, and uncertainty, and download maps and data. On the right is the Extreme Heat Inspector. This app focuses on extreme heat in urban areas. The data being visualized is the extreme heat anomaly for the mid-century compared to present day for the summer over continental US. The charts below show the number of days and nights for the present and for the future that may experience high heat stress, as well as the seasonality of heat and how it may change in the future. These tools are great resources to learn about climate science and future climate change. Visit our websites, the links are there below, and explore the science for yourself.
So as we already mentioned, even though some of the changes for the average global temperature may seem a little bit kind of insignificant, we're talking about 1 degree or some small number, but they can rise to, they can lead to a rise in hot days and or days, for example, as with heat stress, as Jen mentioned. So on this graph, you can see that the just even the last few years, have been the warmest years on record. And 2016 has been the hottest year on record, and 2020 has been the second warmest year on record. So if we continue seeing this kind of trend, then definitely there's a concern about how the heat and the heat waves can affect society and human health. So while temperature is the key, we also have to pay attention to relative humidity, because humidity plays an important role. Colorado climate is relatively dry, but you know, as you go to the south or east, humidity definitely increases the thermal comfort and how do we feel even at the lower temperature. So when humidity is high, the human body is less efficient in regulating the body temperature. And so that's why we have a number of heat indices that incorporate sometimes temperature, relative humidity, radiation, wind speed, and all of those indices are designed to more accurately assess thermal comfort. And so we use those kind of metrics to combine the temperature and humidity to better understand the risk of heat-related mortality and morbidity.
This is a map of the maximum heat index anomaly. Earlier, we were taking a look at temperature anomaly. This heat index anomaly, don't forget that anomaly is just a deviation from the normal. So in this case, our base or our normal is heat index from 1986 to 2005, a 20-year average. And we're comparing it to the mid-century, 2046 to 2065. This map shows greater heat anomalies in the south and the southeast. The Midwest region and the Mountain West also is projected to have more intense summer heat come 2050. Being able to visualize this data, the data originally is a multi-dimensional data format called NetCDF. And NetCDF is often used in weather and climate data. The reason being is that NetCDF is great for storing multi-dimensional data. So we can have dimensions, not only the X and the Y, but also a time dimension and a height dimension. NetCDF can be visualized and analyzed in many different GIS tools, such as Esri tools and some open source tools, such as QGIS.
So again, why do we study those trends and interested in those kind of anomalies is because the heat and climate change are some of the major public health concerns. As I mentioned, more people die from extreme heat worldwide than from any other weather-related hazard or disaster. In the US, according to Centers for Disease Control, on average, 600 people die from heat every summer. The relationship between heat and health are fairly complex. It's not only the weather, but also there is a number of different environmental and societal factors that determines vulnerability and ultimately heat-related mortality. And so our research team has been studying this interaction between heat and health and different factors that contribute to negative health effects for over a decade in a number of US cities. So one of the cities where we have done quite a bit of work, probably over the last 10, 12 years, is Houston, Texas. As you saw in the previous maps, a combination of heat and humidity during summer months can lead to a significant number of hot days and nights. And especially for people who may not have air conditioning, those conditions could be quite dangerous. Houston is also an interesting city to study. It's the largest city in Texas. It's the fourth largest city in the United States. It's the most diverse city in the United States. It's rapidly growing, and there is definitely a lot of different cultures and different groups of people that potentially have different responses and different capacity to respond to heat. So to better understand the heat-related vulnerability and health risks, we use different geospatial data that could help us understand different environmental characteristics and social characteristics. And so here you can see examples of maps that are plotted on a census block group scale that shows the distribution of heat across the cities expressed by the urban heat island. We're looking at distribution of heat health outcomes, use of air conditioning in many neighborhoods, different distribution of race, ethnicity, income. We also use information about age that's not shown here. And all of those factors then go into epidemiological models where we estimate relative risk of heat-related mortality. So it's a really integrative assessment where we incorporating different data and really use GIS as a platform to bring all of those diverse data sets together.
To communicate the result from this research, we developed a tool that shows a spatial pattern of the urban heat island in Houston. We overlaid the heat model output, and we also put in places such as community centers, libraries, and shopping centers. These are places where people can go to get cool. The yellow circles are places that are designated as designated cooling centers. So this tool was developed in ArcGIS Online, and it's currently being used by the Houston Public Health Department to better identify areas of extreme urban heat island and to identify the spatial pattern of their cooling centers.
So again, similar to some of the trends that we have seen for the world and for the nation, if you look at Houston and the distribution of hot days, days in this case over 95 degrees Fahrenheit, we can see that there's a lot more days now than, for example, used to be in 1970s. So, but what does it mean in terms of warning population and how that translates, for example, into some of the actions that cities can take to protect some of the more vulnerable people from risk. So to issue warnings and advisories for Houston, the National Weather Service uses certain thresholds for when they're issuing excessive heat advisory and excessive heat warning. And those thresholds are pretty high, especially for us in Colorado. The advisories are issued when heat index reaches 108 degrees Fahrenheit, and the warnings are issued when the heat index reaches 113 degrees Fahrenheit. So one of the questions that we wanted to ask, especially in the context of climate change, is how the climate change may affect frequency, intensity, and potentially duration of future extreme heat events that would potentially trigger more warnings and advisories.
So to answer this question, we performed data analysis in GIS. Our analysis shows that Houston may see nearly 6-degree increase in summer average daily maximum heat index by 2050, and a 10-fold increase in the number of extreme heat days. These charts that I'm showing here are called calendar heat charts. Months are along the x-axis and years are along the y-axis. The top chart is our present day heat, and the bottom chart is 20 years of under future climate. The darkest orange shows days that would trigger a heat warning. That means temperature would exceed 113 degrees Fahrenheit. And the lighter orange shows days that would trigger a heat advisory above 108 degrees Fahrenheit. You can see that under the current climate, Houston averages 3 heat events over the summer that would trigger a heat advisory. In the future climate, however, as many as 30 days during the summer may be triggering a heat advisory. Another graph available in ArcGIS Pro to visualize temporal data is the data clock. The data clock is a circular chart that divides years into rings, and it subdivides months into wedges. The color codes are the number of days each month that a temperature may exceed 108 degrees, and that's the temperature that would issue a heat advisory. These charts show the frequency and seasonality of heat events in Houston. On the chart on the left, which is our present day, you can see that May, June, and September experienced very few heat events. Most of the heat events occur during July and August. And the number of those heat events every month is about 1 to 3. In the future climate, however, we see the expansion of the heat season and the higher frequency of excessive heat alerts throughout June, July, and August. Using these charts, we can see that in August, heat events will increase in frequency and move into earlier and later summer months under a future climate. These charts, along with the heat charts, are great ways of being able to visualize and communicate temporal data that traditionally is rather difficult to do in GIS. To generate those charts and all the maps that we've showed so far, we developed a workflow in ArcGIS. The native underlying data is NetCDF, and I mentioned NetCDF is a multi-dimensional data set. This data set was a pretty big data set. It started off as hourly data for 100 years from the climate simulation for the continental US. Again, that's a lot of data to work with in GIS. So we first started to think about aggregation. We first did a temporal aggregation of the data, and we went from our hourly data to maximum daily data. Once we had maximum daily data, we then are able to bring that data and read it into ArcGIS Pro, either as points, rasters, or a table, using the multidimensional toolbox. So in this first step, we read the data in using the multidimensional toolbox, and we read it in as points into ArcGIS Pro for present as well as for future. In the second step, we did a spatial join with our county warning areas. So we wanted to join our heat index data to see which heat index value fell within which county warning area. By doing this type of spatial join, we then are able to select only those points that fall within our area of interest, which is the Houston-Galveston area. Once we had that subset of data, we used a really cool tool called the sample analysis tool. This tool creates a table representing data from a multidimensional raster. The output of this table contains all the values from all the times for all the grid cells from our NetCDF raster table. By having this type of a time series table with all the data that we need for the area that we need, we had over 960,000 rows. From all of this data, we're then able to move into step number 4, where we used the summary statistics in order to figure out the maximum value for each day. We used maximum as a statistics type, and we used time as the case field. That generated a table for us that had the daily maximum heat index over that 20-year span. We use this table then for further analysis of frequency, intensity, and duration of the extreme heat events for visualizing the results using the maps as well as the charts.
So as Jennifer just demonstrated, there are some really excellent tools in GIS, not only to work with spatial data, but also with temporal data. And when we work with weather and climate information, especially when we're concerned about present and future and the past, and some of those phenomena could be very dynamic and rapidly evolving. So those kind of spatial tools that help us with spatial and temporal analysis are really, really helpful. And so just in a summary, just a couple of takeaway messages that GIS has been a really great tool for us to better understand, model, and communicate some of the pressing societal challenges that include weather and climate hazards such as floods, droughts, wildfires, and extreme heat events, so heat waves. So, and with changing climate and with some of the major societal challenges that we are seeing in our rapidly evolving and changing world, there's going to be more and more need for geospatial information that can help communities and governments to better adapt and respond to some of those pressing societal challenges. And so today in this presentation, so what we wanted to show is that when we work on this interface of society, science, and geospatial technology, and if we work collaboratively between the scientists, engineers, GIS specialists, it's really exciting and it's really interesting to bring all those diverse ideas in different tools and technologies to the table, because when we bring them together, that really provides us a really unique opportunity to solve some of the complex problems that society is facing right now and communicate the science results to the stakeholders that can make the science a lot more actionable. So that's all we have for today. I wanted to thank you for your attention. Again, Jen and I work on the NCAR GIS program. We put our website here and our Twitter handle. So I think we have some time for questions, either in the chat, or feel free to ask them now, or you can always contact us after the seminar.
Yeah, thank you so much, Jen and Olga. Yeah, we do have time for questions. We have one. Sam preemptively emailed me his question because he had to leave, so he gets to go first. So Sam's question was related to when you're talking about the wildland fires, and his question is: wildland firefighting has always relied on the intuition of firefighters to predict on-the-ground fire, and introducing real-time fire GIS tech could entirely change the field. How soon do you see real-time fire movement GIS tech being used in the field, and who would manage it, do you think? And where can he learn more about projects involving that?
Yeah.
3 questions.
Thank you, Sam, for the question. So that particular project was actually funded by the state of Colorado. So we have developed the fire model, and we are publishing the fire model behavior output using ArcGIS server, and it's available through ArcGIS online tools, as well as through the state of Colorado, their own visualization tools. So right now it is happening. There are some challenges they have to address. So right now it's kind of at the base command. They're the ones who have the internet support, and they've got the computer there, and they can visualize the model output and see that the fire behavior. It is a little trickier in the field, just not necessarily having the cell coverage or the coverage there, but definitely our incident commanders are using this fire behavior. Because one of the really interesting things about this particular fire model, like there's so many different fire models out there, but the one that NCAR developed, this particular fire model, not only uses weather forecast data, but it also uses internal fire weather information, right? The fires that are getting bigger and bigger are creating their own weather. So it's really a multi-component model that takes into consideration the weather that the fire creates, and it creates its own fire behavior. And we're pushing that out using GIS, and it's able to be ingested through GIS tools, as well as through some proprietary visualization platforms currently.
Thanks. What other questions do you all have?
I have one question. That was a fantastic presentation, by the way. Thank you so much. One of my questions was, in terms of making this data available to everyone, I'm curious in terms of how large these data sets are, how they flow with computers that may have not been as have the data as can control it as large as something that you guys would have. So could you shed some light on how working with that?
Yeah, Olga, do you want to address that?
Yeah, go ahead, Jen.
Okay, yeah, so if you're talking about climate model data, you are absolutely right. It's big, and it's just getting bigger. because they really are going. I was just in a meeting today and they were talking about really local simulations, and the size of the data that we're talking about is a challenge. Absolutely. So, you know, so some of the things that we should really focus on when we are delivering that data is focusing on who are we delivering that data to and what is it that they need. Are there ways on the server side that we can subset that data or aggregate that data so that we're not giving everybody, you know, hourly data when really all they want is an annual average? So kind of developing those tools on the server side to aggregate that data, subset that data, to make it more usable for the stakeholders or for the users, whoever they want. That's a big area that the GIS program is really interested in doing, because we really want NCAR data to get out there. We want it to be used. We want it to be societally relevant. And in so doing, we have to address these issues of data size, and making sure that people are able to use it in the tools that they can use. And if we do that, the data shouldn't be too big. If we are able to aggregate it properly and subset it properly on the server side, that hopefully most laptops are able to work with that data, even if they have to tile it up. But that is definitely an important thing to keep in mind when we try to make our data useful.
Thank you so much. I appreciate it.
Great question, Chris. Andrea has a question in the chat. Advice for how you manage work in a crisis discipline. And Andrea, you can unmute and
okay. Can you elaborate a little bit on what do you mean by crisis discipline?
Yeah, thank you guys both. This is really fascinating, and I'm looking forward to diving into all the resources that you presented today. But kind of aside from the work that you presented, but just general advice for, because it's a pretty dire situation, right? Climate change. And so how you get through the day and how you stay motivated to do the work that you do.
That's a really good question. And I think there's actually have been some studies on disaster researchers and burnout, and, you know, just even like the emotional toll that people who study disasters might experience. So I think at least, you know, in our work, you know, one of the goals, you know, for doing this work is not only to document what problems people have, but also what solutions they may have. And that's why, you know, we engage with different stakeholders. We look at a variety of different solutions, whether it's public health interventions or climate adaptations or different vulnerability reduction measures. And so for us, the ultimate goal is to provide something that can be useful and can actually lessen the future impacts. And I think that's really, you know, helping to kind of deal with some of those pretty difficult topics, and especially when we, you know, work in communities post-disasters, whether it's, you know, after Hurricane Harvey or Hurricane Sandy, or in the context of fires or extreme heat events. You know, it's definitely, it could be definitely challenging, but I think some of the people's stories only motivate us to do better work in what we do, so, and make our data and our science more relevant. But yeah, thanks for this question.
I have lots of questions if no one else does. I'll just do one at a time. Quick question. So the calendar heat chart, was that done in Pro? I haven't even heard of that one.
Yes. So the calendar heat chart, it was done in Pro, but it was not done as a calendar heat chart. But that is a new tool that is in there that I just saw. So kind of the way we did it, I had to kind of hokey it up a little bit. But pretty much what we wanted to do, and this is where, you know, it's so great the technology is changing, right? When we created this 2 years ago, the tool wasn't there. But it's a great way of being able to visualize that temporal data. And I don't know if they saw this presentation and said, oh, we should create that, but the tool is there now. Yeah, and it's, we've been at NCAR, some other scientists be using this type of tool a lot for hydrology and taking a look at how, the flow of water, and for temperature and for climate, it's also a great tool for that. So it is definitely a new one that's in pro currently. So
Okay, yeah,
yes.
I've seen that done, but kind of like fudging your way through making a raster and like turning it into a raster is like a TIFF and crazy ways, but this seems a lot easier, so that's great.
Absolutely. That's what I did. I did the raster thing for my output, but now they have it. So it is actually a chart. So
Cool.
yes.
Thank you. And Andrea, you have a
Yeah, sorry, I had another question that just popped up. I was hearing a recent story on NPR about how there's more pressure and more of corporate America is looking at these sort of simulations related to climate change and where they choose to invest. And so I know a lot of the users of the work that you guys are doing are localities, small government, or excuse me, governments, and different publicly supported agencies and universities. And I didn't know if you guys have been contacted at all by corporations or the private industry for these sort of products.
Yeah, that's a good question. Jen and I work in the Research Applications Lab, which is one of the NCAR's labs. And there are definitely some partnerships with private sector, with private organizations who are interested in either forecasting capabilities or climate-related information, climate services, especially I think when it comes to organizations like World Bank or some of the reinsurance companies that kind of interested in more long-term scenarios. A lot of our work is funded by, at least the work that we have presented today, really has diverse funding. Like Jen mentioned, some was funded by the state, agencies, others have been funded by National Science Foundation or by NASA. And so whenever we work with public funding, like, for example, the National Science Foundation or NASA, we make all of our data and products publicly available, so then communities can use that data and information for free. And if, sometimes, if, for example, we develop something for Houston, but then we can apply the same methodology for different locations. So, that also can be applied. But I would say, at least in our work in the GIS program, most of our funding has been either from the government agencies, state, local, federal, and maybe less from the private, but you're absolutely right. I think the interest in this kind of a data and services is only going to increase. So we're definitely interested in partnering with both public and private sector.
I'd like to add on to that question a little bit in terms of gathering data and compounding it. What biases could come in whenever you're working with these data sets and compounding it all?
Can you elaborate a little bit what you mean by biases?
I'm just curious with like where the data could be stored, if there's anything that someone would potentially raise an eyebrow to and be like, well, I don't really know, or something. And it's fine if there isn't. That's completely acceptable too if you can't think of anything, which I would imagine is a great thing too.
Yeah, so I think, one thing to address any kind of questions about the data. So, just wanted to put a plug in for metadata, right? So metadata and documentation, because some of the tools where, like Jen showed, Climate Inspector or some of our climate change portals, some people may, look at the data and say, how do we trust that? And, what does it mean? And so, our goal is just to be really transparent and just to present scientific data just as they are. They've been peer reviewed. They've had, data that come from community models. We provide links and references to that information. And we always, make a disclaimer that this is a research model. These are the uncertainties that are associated with that. But we also want to emphasize that there is so much scientific evidence and consensus about climate change and some of the changes in extremes that even given all the uncertainties, the society can still take actions and start preparing. One thing we address that uncertainties, we're looking at the range of scenarios. So we kind of look at how do we visualize uncertainty. So that's also an active area of work that we engaged in, and it's pretty challenging, but it's also exciting. So I don't know if I answered your question, but
yeah, that answers it really well. Just because as unfortunate as it is, I feel that climate mapping and any climate study that's proving that the globe, like the world, is heating up, and people are always skeptical about it. So I was just curious what steps you've taken into that, even though we're all very aware of what's actually happening.
yeah, definitely. So I would say definitely documentation, just demonstrating the scientific process. And I think visualizations do help people to connect to this information, and talking about climate change by discussing weather, because most people experience climate through weather, right? And so even if you look at the last 10 years, regardless where you live, people may have seen, different patterns, whether it's, tropical storms or wildfires or droughts. And so talking about some of those changes definitely help to convey the message.
I like that you brought up metadata because it's something we teach in class, but I think it's something that students don't really think real people do, but you should. I had another question. So you brought up a lot of different things, of course. You talked about the 3D modeling with City Engine. You talked about NetCDF. I think all of what you did was in ArcGIS Pro. For someone who's trying to get into this realm of science and visualization, what advice do you have for what skills they should learn, what technologies they should learn? Is it all in Pro? Did you do anything in like R or anything, any coding that they should learn, things like that?
Yeah, so that is a great question. And I do find it's a bit of a hard question to answer now, given all the advancements is in the geospatial technology. But at least everything I did was in Pro. So that is a great tool, and it really is an expanding tool with a lot more interoperability with different types of data sets, which is great. I use Python every single day in my job. I wouldn't be able to do anything without Python. So that is a pretty necessary skill, I think, moving forward in the GIS field, just to be able to, because you're always kind of having to replicate kind of your process. You need to automate your process. So that is a really great skill, is using Python. The nice thing with Python too is we don't just, I use a lot of Esri, but I use a lot of open source as well. And Python is also the language for open source geospatial technologies. So I use Python for GDAL and for different NetCDF libraries as well. So that's key. And the visualization thing is really interesting. I think Esri's visualization is advancing, even from 2 years ago when I developed this, even in Pro. The visualization technology is advancing in Esri. So there's a lot that we can do there in 2D and in 3D that I couldn't even do 2 years ago. And web-based visualization is also really expanding. So, that's also an area that I feel like I still need to kind of keep up to pace with, is the web, because that's how everyone is expecting to see the data now. People aren't necessarily going to have Pro on their desktop to visualize your output, but you need to make something interactive. So kind of keeping that in mind as well, is the dissemination of your visualization and your data is also key.
Awesome. Thank you so much. Well, we are officially out of time, so I'll stop recording and officially dismiss the class. But if anyone has any final questions, if Jen and Olga have a couple minutes to wrap that up, that would be great. And I just want to say thank you so much. This was really great. And you touched on so many things that we've touched on in this class and in other classes, especially Python. We have a whole class on that, so take NR 426. And yeah, thanks again, and I hope everyone has a great day. Enjoy the weather. Not the climate, just the weather.
Just the weather. Well, thanks everyone for coming, and thanks for having us to present. Thanks, Beth.
Yeah, thanks, Beth.